by correcting something I said last time. So first I need a definition. So, a spectrum. E is a field if E star X is a free E star module for all X, Spectra X. Okay, and last time I said something about the Kuhn isomorphism, which wasn't the fact I was trying to think of. The fact that I was trying to think of, this is a theorem whose proof is in Localizations 2. It's not very hard. Is that every field E is a wedge of suspensions of Kn for some n. Okay, so just wanted to correct the statement. Okay, so the GANs are like the prime fields. They're like the indecomposable fields. Every other field is built out of this. All right, so then back on track. So this was just a correction from last time. Okay, so I said last time that I would start this lecture with motivation, okay? And Greg gave part of my motivation. And last time, but he did it really quick with a diagram that, did I make a mistake? I'm seeing all kinds of...
And what about ordinary cohomology with coefficients of theory?
These are like, so HFP, or
HFP
they'll
to
be
the
wedge of
n,
infinity or HQ, yeah.
HFP to the n, for example.
That'll be, so I think that'll still be a wedge of HFPs if you forget some of the structure, right?
Oh, okay.
Yeah, okay.
I mean, in algebra, if you have a product of fields, it doesn't have the free property.
So this is the definition of what it means to be a field, right? In Spectra. So I'm not saying anything about, I'm just saying like, this is what I mean. If I'm gonna call this a field. This is the definition of the word field for Spectra if all of the modules are E star free. So.
But I mean, that in algebra, if you make that definition, then a product of two fields isn't a field. Because, sorry?
So maybe the question is if the element magnetic spectrum of the broken field is a field in this sense.
Yeah.
I don't know. I'm not.
I mean, if you have a wedge of things and you take one of the factors as a module, that isn't free.
So.
Well, that's okay. So it doesn't say that every wedge of suspension is.
It goes in one direction. A field has the property that it is a module over Kn, and then it decomposes into a wedge, but not the other way around.
Okay, I'll think about it.
Okay, like, I mean, so I guess the lemma you prove is that if you have, so I think there's a confusion maybe about the logic, but like if, so the proof goes is if you have, you take E, you smash it with Kn, and then you actually prove that this definition implies that if you take E smash X, it's going to decompose as a wedge of suspensions of E. So then you smash these two with Kn, and you smash this with Kn, and you observe that, well, okay, so first you observe that because E is a ring, Kn star of E is not 0 for at least some n, and then so then you pick that n, you smash these together, and because Kn is itself a field, Kn satisfied, it's split as a wedge of suspension of these things. So I'm not sure about the comparison to algebra. I don't think
Could you give an example of such a wedge?
Can I move on instead? I'm sorry, like I did not prepare an example, so maybe we can talk about it afterwards during the coffee break. Right. Okay. So the theorem that I want to state and I'm restating it for, Smith. I'm restating, I'm gonna give a bit more detail about the statement that Greg gave last time. So I wanna define CP comma N to be the x's, so this is in the category of finite spectra. These are like in the you restrict to the compact objects. So this thing, so for each p, right, I have a Morava K-theory. So I want to look at the subcategory where the cohomology of x vanishes. Okay, so one can show that this is a thick subcategory. Okay, and here I'm taking 0 is less than n is less than or equal to infinity. So I'm including the HFPs in there. And maybe an observation is that K0 is the same for every prime. So that means that these are all the same category. So these are all the x's in A to C, such that the rational homology of x is 0. Okay. So instead of having a bunch of names for the same thing, I'll call it C01. Here I'm using the names, the double index are the names from Balmer and Sanders' paper on the thick subcategories for G spectra for certain G's. Okay, so then the picture that Greg drew had a bunch of dots in it, and the dots were precisely these things. Okay, so then I want to be able to draw a picture. And then the theorem is that this is Agnes Beaudry. Let me just do pass, and back in the day it wasn't called the Balmer spectrum, but now people call it the Balmer spectrum of SHC is as follows. So I'm going to draw a picture, and the picture will contain more information even than before. So I have. Let me start with 2. Okay, so these are contained in all of the finite ones, and so here I have C2H, C2H minus 1, and so on. The containments were, I think it's Steve Wilson, or Steve Mitchell with the containments, okay? So C2, I guess this would be 2, and then they're all contained in this C01. Okay, so if you care about studying the triangulated structure of some categories, some cool categories, and you somehow care about spectra, then you're sort of forced to care about these Morava K-theories. Okay, they detect all the primes of the category of spectra, so the primes can be completely described like that. So that's also one of the reasons why people often call the KHs, the Morava K-theories, the primes of spectra. Okay, so the picture was already there on the board yesterday, so I won't say much more about this, but I wanted to tell you what the dots were in there and how their precise relationship with the Morava K-theories is. Okay, so, and there's other reasons to care. I mean, the thing about fields, that's an interesting result. There's also like theorems about, so you have a ring spectrum, so its homotopy groups are a ring, so that's what just a homotopy ring spectrum. And then you have some elements, and you ask, okay, which elements are nilpotent? Okay, so the nilpotence theorem of Beckmann, Hopkins, Smith says that, well, okay, so mu detects nilpotence. So now it is nilpotent if and only if it's nilpotent in mu homology. Okay, but then you're like, okay, mu's a big theory. Okay, it's nice, but it's big. Is there like some more refined criteria? And then, one of the criteria is that, if you're nilpotent in Kn homology for all primes, p's, and odds. Okay, So they also get, the Morava K-theories also give you criteria for nilpotence. And these criteria for nilpotence sort of translate into studying stealth maps. If you have maps of spectra, when do they iterate to 0? And that's sort of, these kinds of constructions are the kinds of tools people use to then construct periodic maps in the stable homotopy groups of spheres. So this sort of brings us back to this first, the first thing I wrote on the board last time was that there's like the geometry of formal groups governs periodicity in the stable homotopy category. So it's sort of already the nilpotence theorem drags you back there. Okay, so that's the first thing. Now, the next thing I want to do, so now we've like established that we're going to call these primes. What do you do with primes, right? Like one thing that we love to do in algebra is localize the primes and study our problems p locally, and then try to, or p, in the p local category context, and then try to glue back the information together. So now there are notions of localizations in spectra, and that's the next topic that I want to overview. I want to give you the definitions so that the things I write aren't so mysterious. So how do we talk about localization in spectra? So with these, I guess. Everything I'm going to write, they're all going to be spectra. I'm sorry if you're still not loving spectra, just treat it as a, really I'm thinking the statements I'm going to be making are mostly in the stable homotopy category, so think of it as a nice TT category. So that can get you a long way, actually. So now we're going to call X is E acyclic if E star of X is 0. Okay. So you're E acyclic if the homology of E with respect to X is 0. And so I think that maybe this has not been said yet, but if I, go into the orthogonal spectra category, Stefan told us how to smash them, told us how to take homotopy groups, remember to take the group to be trivial, and the E homology of a spectrum is just the homology of E smashed with X. Okay. Now, why is E local? If for all E acyclics, the maps from X to Y, these are 0. You're local if you don't admit any non-zero maps from an acyclic. And we're going to let SHE be the full subcategory of the local spectra. Okay, so here's an exercise, and I don't know if there's a problem session, but you can think about it. So let's let F of the local spectra, then F is a weak equivalence. Okay, so just as a reminder, being a weak equivalence means that you're an isomorphism on pi star for all stars. Okay, so if and only if F is, so if you take E star of F, this is an iso. So in E local spectra, the equivalences are detected by E star. Okay, so E local spectra is a category where you've restricted to the maps that, you've restricted to the full subcategory where equivalences are detected by your homology theory. So it's a localization in some sense. So I'm going to say something else just now, but we'll see that it's a localization. So really what happened, this is like an analog of just inverting all the Easter isomorphism. But for that to be true, you sort of need a functor, right, that localizes. So that's the next statement that I want to make. So first let's say what it is. And people call it a Gauss field, localization of Z at E is an arrow. This is a map from Z to an object, such that, so first you want that E star of the 8 is an isomorphism. Okay, so this is an E equivalence. I haven't asked that Z is E local in this case though, so this may not be an actual equivalence. Okay. And the second one is that for any map, so if I map Z to a spectrum Y, so where Y is E local, so then there's going to be a factorization. There's a factorization. On the side. Okay. And then the theorem of Gauss field. Is that localization exists in our functorial. Okay, so let's see how I phrase it. So there's a natural localization functor. H to E, and then I guess the natural transformation. So from the identity to okay, so now I want to go through some examples. So let's start with G. Let G, yeah.
Is LE set supposed to be local?
Is what?
LE set.
Oh yeah, thank you. Yeah. I don't know what comes before I. Usually I put 0 here. And LEZ is local. Thank you. Okay, let G be an abelian group. And then we're gonna let SG be a Moore spectrum for G. Okay, so I'll tell you what that means. So the first thing is that the homotopy groups of SG are 0 if I is less than 0. And then the second one is that the homology, so the homology of SG, so is gonna be, oops, I don't want capital, I want capital S, bold S, not bold G. As G is gonna be G if K is 0 and 0 otherwise. Okay. So you can construct these by taking, if you've seen Moore spaces, so Moore spaces are spaces that are determined by their homology, okay? And then the suspension functor plays well with homology, so you can take a Moore space, suspend, take the suspension functor, the suspension infinity functor, and then sort of move it around using the tap to triangulate structure to put it in the right degree. Okay? So these are not terribly mysterious in terms of their homology or how they construct, but in general, it's not, for a generic G, it may not be easy to compute the higher homotopy groups or anything. Okay, so then I want to look, so examples of Moore spectra is if you take G to be Z mod P, right? Did I do this right? Right. If you take G to Z mod P, then you can construct it. You take the sphere spectrum, it has a self-map, which on homotopy on pi naught looks like multiplication by P, and then you can take the co-fiber, so you take a triangle, it fits in a triangle like this, and this object is a Moore spectrum for Z mod P. Another example is you take G to be the integers localized at P, and then again you take this multiplication by P map, but instead of stopping, you keep going, and then you take the homotopy colimit of this, and so this is what people call the P local sphere, okay? And this thing is, this is C local P, and this is called the P local sphere. All right, so these are two examples of Moore spectra. Okay, so let's look at what localization functors look for these. X localized at P. It turns out that, okay, so this is going to be the notation that we use for the localization of X at P. It turns out this is equivalent to X smash with the P local sphere. Okay, and so the theorem of Balmer is that if you look at the homotopy groups of X localized at P, then this is going to be the same as you take the homotopy groups of X and you localize those at P. And also a P local spectrum, so X is P local, if and only if it's homotopy groups. Are uniquely divisible. Okay. So you can completely recognize P local spectra by their homotopy groups, and localizing is not that bad. Okay. A localization that has this property that you localize a sphere. So, okay, so SP, I should have said, P is itself P local, and so this is the same as, the sphere spectrum. So localization that has this property that it's just take the thing and smash with what happened what you got from localizing the sphere spectrum. This is called smashing. So this is smashing localization. we'll see more examples of those. Okay, so similarly, you can, so x sub q, this is common notation for the localization of x at the rational Moore spectrum, okay? This is also smashing, and so it turns out that you can just smash with the rational Bernoulli spectrum. So, and what does this do to homotopy? So this rationalizes homotopy groups.
So X is P local, you need to be divisible, P divisible for Q divisible for Q, not equal to P.
Oh yeah, sorry.
And also maybe you made a different definition of this localized at P.
Yeah,
You want to invert all the other primes?
Exactly, yeah.
Oh my God, yes, that's what I wanted to do. Oh, thank you. Good. Yeah. All right, so wait, we can still do it this way. We're gonna do 2. Then we're gonna do 2 times 3. Then we're gonna do 4 times 3. Then we're gonna do 4 times 3 squared. That's 8 times 3. 8 times 9. You get the pattern? Oh wait, I think I just need to do 2 times 3. 2 times. I think I just need to do this. 2 times 3 times 5.
Miss out here, yeah.
Yeah. Okay. So we're gonna do it that way. That is. Oh wait. So we're supposed to skip a prime. Okay. But then when we get to that time when we're supposed to repeat it, we're gonna skip. Okay, so then we're gonna 2 times 3, 3 times. Okay, and then we're gonna skip P. This is how we skip P, right? You can't really put P plus 1 there, but okay. So this is a trick for anybody on the primes. Okay. Good. In general, if you want to localize a way, you want to localize, this is always confusing, right? You want to localize at a set of primes, which means you want to invert all the primes that are not in that set, okay? You have similar statements. You can do this trick, you can just omit the primes that you don't want to invert, and then you have a similar statement like this. Okay, so the next one, so this is all like, now you're telling me, okay, well, this is just like really just localization, okay? The next example that I'm just gonna say the facts of is that localization also sort of behaves like completion sometimes, okay? So it both behaves a little bit like localization or like completion, depending on what the theory you're localizing at are. Okay, so I'm gonna let x sub p. Sometimes people also put a little wedge there to denote the completion, but I'm just gonna not do that. Okay, so this is gonna be, by definition, you localize at this other Moore spectrum that I gave you. Okay, so the Moore spectrum, and it turns out that this is, and my inverse limit. This is how we're going to do it. This is the inverse limit over n of x. So a diagram where s c mod p to the m, and then x slash, I didn't give myself enough space, z mod p to the m minus 1, and then dot, 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 okay? So for each z mod p to the m, you have a Moore spectrum, okay? And this construction of Moore spectra, you can, if you have a map of groups, you can get a map between these Moore spectra. So you take the spectrum for this system, z mod p squared, z mod p, blah, 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 okay? You take the Moore spectrum for this, you smash with x, and you take the inverse limit. It turns out, Bellsfield shows in his paper that these are equivalent, okay, for this localization. So XP is kind of like, if you know the definition of P completion, I mean, you're kind of staring at like a Spectra version of it. So XP is like P completion. So, but you do have to be careful about the homotopy groups. It's not true that for a general X, the homotopy groups of the topological P completion is going to be the P completion of the homotopy groups. Okay, so they're a counterexample. However, if pi star of X is finitely generated in each degree, then this is fine. P is so, and by this I mean the P completion. All right. So that's weird, but it's the way it is. Another fact is that, so another, like I gave you more spectra, like what about localization at Allenberg-MacLane things, but so maybe another fact about this completion is that if X is connective, okay, so what does that mean? So that means that pi I of X is 0 if I is small enough, okay? Then the P completion is also equivalent to the localization at the mod P Eilenberg-MacLane space of X. Okay. Yeah.
Is the statement when pi star of X is finitely generated, is there something about the lim one vanishing?
Yeah.
Or is
It's a lim one thing. There's a lim one thing. Yeah. Okay, so all of this stuff is in Bousfield's amazing paper, which is called Localization with Respect. Okay, it has localization, okay, but that's not enough in the title. It also has cohomology in the title, because there's like a localization for spaces paper, which is like part 1, and then a localization for there's lots of examples and whatnot. Okay, so now the last thing I want to say is that, and also appears in that paper, is that there's a local to global principle. And the local to global principle is that there's a homotopy fullback square. Okay, so X goes to, you can take the product over P of these completions. You can go to the rationalization, or you could do it in the other order. Well, I don't know. Don't. Here's what I mean. Not really. Go here, and this is a pullback square. Okay, so if you don't know what a homotopy pullback square is, one thing it buys you is Mayer Viator sequences on homotopy groups. Okay. So this is in. Okay. So so because of this, you know, so I guess this is like local to global. Because of this, it's customary to just fix a prime and try to study, well, you think from this that you tried to study P-complete spectra, but really we fix a prime and we study P-local spectra, and then we hope that, you know, we can put these things back. Okay, but there are other primes, right? That was the whole point of the last lecture, is to introduce the K-theories. So now, going forward, I'll just fix a prime, okay? And I'll stop repeating it. And if I make statements, it'll be, so let me write something. So we're gonna fix P, and we're gonna really be restricted to, this is P local spectra. And okay, so what does that mean? That's S, okay, what did I call it? SP local spectra. Where Alright, so now, yes. What about the LKHs? Or the other things? No, we've already talked about LK0 because K0 is just HQ, and I've said something about LK infinity because this is HFE. Okay? But then there's all the other ones. So for example, what about localization at mod P K theory? Or what about localization at K theory? You know, at P local or P complete K theory, or these kinds of things. I will get to these, but first I want to make a definition. So we let LH be equal to L of the wedge of these things. So you take the wedge of the first HK. I guess H plus 1 Morava K-theory, so again, my prime is fixed. Okay, so now these localization, they're hard to describe in general, okay? It's, you know, understanding LH of S naught is like the goal of my subfield of stable homotopy theory in some sense. We can say a lot about it when H, well, if H is 0, we're done, it's just rationalization. If H is 1, okay, so I'll say more later, but if H is 1, we can compute the homotopy groups of the P local sphere. And then if H is 2, we know the homotopy groups of the localization of the sphere here for primes. They're written down in the literature for P greater or equal to 5. Okay, so, and then after that, well, it's pretty hopeless at this stage. Okay, so we need new technology, or just to start caring about other questions. Okay. But maybe like it is this. It's so maybe like a remark is that if X is an MAUP module spectrum. Okay, the word, if you were happy with these words and then spectrum just like, you know, made you feel nauseous, then again, it's a triangulate category, you have a smash product, you know, it's like being a module means that you have a certain kind of multiplication, so you can phrase that categorically and then you do the same thing, okay? So just pretend like, the best thing you can do for yourself is pretend like you understand because you understand algebra, okay? Until you have to prove something. So then, in that case, LH of X is going to be equivalent to, you take this element VH that I defined last time, and you just invert it. So for modules over MU, this localization isn't all that mysterious. It's just literally looks a lot like some algebraic localization, right? Like picking out an open set somewhere. And that's what it is. This inverting VH is equivalent to picking out an open set in the moduli stack of formal groups. Okay? So for MU module, it's a lot more concrete, but then, you know, it gets more complicated later. And maybe a remark is that LH is smashing, which means that LH of X is the same as LH of S naught, smash X. Okay. Did I make a mistake?
I think that remark is not make it a bit more complicated maybe than But I think if you're torsion, then it's correct. I mean, if you are IH torsion, then it's true.
Right.
Otherwise, it's a bit more complicated.
So there's moments when it's like literally in group VA.
Like if you're type N, how's it bigger than N that doesn't true?
That's what type H, yeah, for some reason. Okay. I don't know I feel like I'm. I'll talk to you after. It's totally something is confusing. Okay, so here's another fact, is that LKH localization is a kind of completion of LH localization. Okay, so if I want to compute LKH of X, and I already know how to do LH of X, then I can snatch with, these type complex that I haven't talked about, but roughly it's like, you take F, S, and you smash, what I'm writing makes sense for some choice of I's, and so not so for some choice of I's, but so for many of them, and for some cofinal choice of I's, where these all go to infinity. So let's call this sequence I, so I, and then LKH of X is like this completion. So you're kind of completing with respect to the VI's before the height that you have. All right, so these completions, these localizations are complicated, but that's okay. Otherwise, I'd be out of the job. Okay. So maybe an exercise. I don't know. Again, I don't know if they're going to talk about it in the problem session, but this is something that you can do from the definition. Is that there is always a map from LE wedge F of X to LE of X. Okay, so in fact, so this map is, I mean, I guess every time I write something like that, people are like, what about the zero map? I mean about the zero map, at least most of the time. So this, what I mean, this map is the E localization for X. Okay, so all right, so that means that, for example, right, I always have a map from LH to LH minus 1 because, I just dropped a wedge factor. And I always have a map, I'll do something fun. Okay, H minus 1. And I always, I don't want to put it there. Okay, I want to put it there. Okay, there's always a map like this, okay? And I could drop all the first factors and I get a map here, okay? So now let's stick some things here. So I get maps like this. And so now this wants you to finish it into a square. So this is actually a homotopy pullback square. And the bottom corner is this. So first you K localize, then you H minus 1 localize. Look, these ones are not of that kind, right? They're not of like local. So this is, the statement here was that this is X. In this case, I took the complementary factors. Okay, so this is a homotopy pullback square. Okay, again, if you don't know what that buys you, it buys you the torus, okay? So you can compute the homotopy groups of the top corner if you know the homotopy groups of here and enough about the maps and the structure. I guess the next word was, it was returning to the next word, but that's okay. And now, okay, so here's a theorem of Ravenel and Hopkins. I guess it's Hopkins-Ravenel. So this is called the chromatic convergence theorem. Okay. So take X and we're in P local, okay? And then X is the homotopy limit of So, right, I'm taking these maps here, and I'm assembling them into a tower. So, all right, so let's put these, okay, and then like, what is that? What does that buy you if you don't know? I mean, it means that you can build X out of these intermediate localization, and then on homotopy groups, if you take a homotopy limit, you get like an limit sequence statement. Okay? So, again, you can reconstruct this information about X from the previous ones. So now, okay, so what do we have? We have, I can take X is going to be the inverse limit of these LH localizations. But now, every time I want to go from a lower localization to a bigger one, right, then I've got a little homotopy pullback square that tells me that I can reconstruct this next layer by this sort of localization at a single prime, okay, together with some gluing data, which is like the rest of the square. Okay? So these prime localizations, so maybe like the philosophy that you get out of this is that X can be reconstructed. So, and here I mean X finite from its Morava K-theory. So here, now we're taking all primes and all i's. All right, so that's a very philosophical type of statement. If that's your plan, you probably get stuck with us at 2, at h is equal to 2, and then you can, join the family. We have lots of fun. However, there's lots of, there's a lot of space. There's a lot of space in the theory for more theoretical and for abstract statements. So for example, like one conjecture is that this map here is split. So that this is a wedge summand of this. Okay, so this is called the chromatic splitting conjecture. Okay, and nobody has a clue how to do it. Okay, yeah, that's such a beautiful, simple statement. Okay, and there are like analogs of this statement in algebraic context that are true. You can talk to Toby if you want to know, and his collaborators. So that's like, so I don't want to write this like that. We don't know if it's split. So the CSC, so the splitting conjecture says that iota is split. Okay, it's true everywhere we were able to check it. And yeah, so there's a lot of open questions. They're very difficult. So it feels like we're missing some big idea here to start being able to answer our questions in a non-computational way. Okay?
Could you say a little bit why one expected that should have been splitting?
Because we computed it and it happened. It's literally like that.
High-level researchers, it always happens to be the case.
Say that again?
Well, there is no kind of conceptual reason that you expected this. You computed it always.
Maybe, okay, so it could be that now there's like, I don't know, I don't know all the work of the algebraic categories, like when this happens, why it happens. Okay, so I guess that would be the first place to look. But like historically, it was just like, oh wow, it splits.
Okay.
Great, and this is how we work in this field. We check it at 1, we work really hard to check it at 2, and if it survives, well, we keep calling it a conjecture because at 1 we already decided this was a conjecture. So yeah. So no, it's like there isn't. So it could just be a fool's errand, right? But
You have H, F, HFP as a sort of thing at infinity, and that just doesn't come into the Hopkins-Ravenel thing.
This one?
Yeah.
It doesn't really come in there.
Yeah, so you can ignore infinity.
This is just for finance. I think maybe this is the reason why I needed the compactness there. That this isn't true in general.
Good.
I think, so.
Thank you.
All right, so let's see. Maybe just a parting thought is that this pullback squared, I mean, it mirrors a situation on the moduli stack of elliptic formal group laws, okay, where you have these formal group laws, and we define the notion of height. Okay, so you can talk about formal group laws. The height was at you had to be over a FP algebra, but you can kind of generalize that and have like a notion of height less than or equal to something. Okay, and this bit is like F less than or equal to H. This thing is like, you look at things that have height exactly equal H, but then you look at a formal neighborhood of this. So NFGL less than or equal to H minus 1. And now this is, you take and this is the thing that you take this, and then you look at the things that are less than or equal to H minus 1 inside here. Okay. And now the picture it has a different variance. And then, so there's a statement about having like a push out of stacks. I really don't want to say much more about this just because I don't know how. But you can ask your question. But if I say I don't know, I really want it to be I don't know. Go ahead.
I was wondering is there a splitting on the level of the moduli stack?
Yeah, not that I know. Yeah. Okay. All right, so I have some time left. So now, for the rest of this talk and then the next talk, I really want to focus on this KH localization. And the first talk I told you a bunch about formal group laws, right? And now I just went in and told you a bunch of facts. These are all pretty substantial theorems, and you should go look at Ravenel's 1984 paper on localizations. Well, it says localization in the title. And but except for defining the KH, we really haven't touched back with this formal group law story that I gave you earlier. Okay, so now I want to go back and talk about the formal group law story a little bit more, and really talk about how the formal group law story really tells you ways to compute these localizations. Okay, again, difficult and mostly inaccessible way past height 2, but still, it's like a beautiful story, and it connects to the group cohomology also. Okay, so that's my next goal. So I'm going to start just because if I start now, then I can say more later. So I'll start with the next topic. So maybe like the hint that the words deformation theory were going to show up was that here I took like some formal neighborhood of some strata on the moduli stack of elliptic curve, and the point is that if I think about that algebraically, then I get a story about formal groups, and then there's a mirror in topology. So the first thing I want to do is I want to get rid of all my gradings. Okay? So remember we had KH star, and this had these homotopy groups, and it had a formal group law, which I denoted by FKH, and this time I'm gonna work. If you're more careful about your definition, then you can actually arrange things so that so you can arrange things so that the P series is exactly that, no higher order terms, okay? So before I had plus dot dot dot, so I'm gonna arrange it so that I'm gonna pick my KH and I'm gonna do my quotient. The KH was like some quotient by generators of a U, right? Like, it's a polynomial ring, there's lots of choice of generators. So I'm gonna make a choice that allows me to just have that. I'm not telling you that you should see why that's possible, just that you should believe me that it's possible. So then I'm gonna do that. And then I'm gonna look at the map from KH star to, now I'm gonna, not only am I gonna kill the grading, but I'm gonna give myself roots of unity. So I'm gonna go to P to the H, okay? So this is gonna be, let's just call this a little k, this is gonna be my field. And this map, I just wanted to do, well, what it should do on FP, and just send the H to it, okay? Sorry. I'm just getting rid of my grading so that I can tell a clean story. So, and then I'm gonna let gamma H be the group law that I get from, let's call this, I'm not gonna need this map very long. These are, okay. So I just take the formal group law and I apply this map to all the coefficients, okay? So now I have a formal group law that I'm thinking of living over. So now this thing is in K11, 2, okay, and I've killed the grading, I'm not thinking of this as a grading yet. Okay, so this is called the Honda formal group law. Of type H. Okay, so now here's the next thing I want to define is a groupoid, okay? So we're gonna, well, I guess first I should tell you what, so we're gonna let B be a complete local ring. So, and the maximal ideal, I'm gonna denote by M sub B, I guess would be better notation. Let's just assume that I guess I'm calling this K. So I'm just gonna assume that I've made an identification with the residue field ring, residue field of B with K. You can relax this, I'm just not gonna get into the concept. Okay, so I've chosen an identification, and I'm gonna let Q from B to B mod M be the quotient. I guess I'm calling this MB. Okay. So now so now I'm gonna let Jeff be I guess it's probably better like this. I'm gonna let deformation of gamma over B be the following groupoid. Okay, so the objects are going to be formal group laws G, so a formal group law, such that Q star of G is equal to M. So it's gamma H, but I'm fixing my height, I'm fixing my gamma, so I'm just going to call it gamma. Okay, so what does that mean? You have a formal group law over this complete local ring, you reduce all the coefficients modulo the maximal ideal, and you just get this formal group law gamma that I picked. Okay, this is called the deformation. Yeah, go ahead.
Q seems to be going the wrong way. Q star seems to be going the wrong way.
So it's this, you would have preferred if I let Q lower star. This is I have G as a formal group law over the bigger ring, and then I take the coefficients, and this means mod out the coefficients by M. And then I get gamma. Gamma is a formal group law.
Okay, so it's covariant. Okay.
It's covariant here. The reason I write it as upper star is that really this is like supposed to be like spoof of, like what's a formal group law? It's a group law on spoof of something. Yeah, so I'm just, I just mean like apply. But I know that's confusing. It confuses me too, but you know, one day I just accepted. Okay, so now that's called the deformation, and I haven't told you what the morphisms are. So the morphisms, it turns out, are just going to be isomorphisms. So I'll write that and I'll stop. The morphisms are going to be isos F from, G1 to G2, such that if I apply Q, if I reduce the coefficients mod,
Can you raise the ball?
yes, I can raise them. So if they're going to be isomals such that if I reduce the coefficients modulo the maximal ideal, I just get Y again. So in other words, this is the identity. So there are isomorphisms that look like the identity modulo the maximal ideal. So this is a groupoid, and next time we're going to talk about that groupoid and some general theory about it. Okay? That's all I have time for today.